Okay, hello all you crazy people out there. My name is Michael. I like wizards and dragons and making games, and let's talk about making 3D games in GameMaker run fast. So, this is the big one. This is the one that most of you have probably been waiting for. This is probably the most dramatic and also most common thing that people do to make their 3D games in GameMaker run faster. And that is the subject of combining a bunch of small vertex buffers into a single large vertex buffer, or a small number of large vertex buffers. So this is part of a multi-part series on videos that I'm making on things that you can do to make your 3D games in GameMaker run better. For the uninitiated, I recommend going back and watching the first one, especially, and also just all the other ones, because it's good to have a general understanding of these things. But the first video especially is going to be an overview of how this is going to work, how this project is going to work, the different things that can make your game slow down, as well as just some general vocabulary words from when it comes to doing 3D things in GameMaker that you're going to want to know. So this is a project. It's full of trees. There are 2,500 trees in this project. They're drawn at random positions. I've done a little bit of changing things since the last one of these videos. Right now, this is how this is set up. Each of the trees is stored in in basically a struct. There is a tree data array, and each index in the array for each tree on the screen contains a struct containing the model, which is just the vertex buffer that we're going to be using, the texture, which is redundant, the texture, which is going to be sprite get texture, with the tree sprite texture. That's a hard one. There's an X position, Y position, and a random rotation between 0 and 360 degrees, or 0 and 2 pi for those of you who prefer that. And in the camera's draw event, at the bottom, we're just going to be drawing each tree. For each element in the array, get the struct at each position in the array, and then matrix build based on the data's x, the y, 0 on the z-axis because all the trees are flat on the ground, and a random rotation, the random rotation that was assigned in the create event over here. And then you just draw it. No, I'm not going to be bothering to reset the matrix to the identity matrix after this line of code here, but I am going to be building the matrix every time we go through the loop here in the draw event, instead of caching it elsewhere like I was in the video about matrices not too long ago. Okay. So if you saw it just here, it looks like this project as it is averaging about 200 frames per second, about 200 FPS real. It may creep upwards a little bit as the game runs for longer, because the first frame of the game always takes longer to appear because it has to do a lot of initialization stuff. But we'll say it's hovering at about 210 FPS real. If I were to run this on the Raspberry Pi, because I would like to do my side-by-side comparison between how the game performs on my computer here and on a Raspberry Pi with dramatically different hardware capabilities, I want to say this is going to run at about 20. So once it settles out a little bit, 16, 17, okay, it's running at about maybe high teens FPS real. And if I were to move the camera around, you'll get a better view of what's going on. You'll see it's more or less the same. It looks the same. All the trees are in the same random positions, and we're getting about maybe high teens frames per second, both the actual frames per second, like the number of times the screen refreshes, and FPS underscore real. Okay. Let me kill that process so that it's not running in the background and make my Raspberry Pi heat up. Boy. I hope I don't forget to say anything in this video, because this is probably going to be a little bit of a long one, and I've tried to record it like 4 times. And different things have gone wrong every time, and I really want to get this video out by like today. It is what it is. So let's start by talking about exactly what's going on, and maybe some of the things that we can do to make the game run faster. So GameMaker language, as you may or may not have heard, is not the fastest computer language in the world. It's certainly good enough. You can certainly make games with it. It's not like cripplingly slow. If you want your player to walk around the overworld or whatever, you can certainly do that in real time. But if you have an array of 2,500 trees that you want to iterate over and draw them in every frame, that might start to get a little bit expensive. You can optimize this a little by using regular GameMaker objects instead of just structs, but I'm not going to be getting into that today. GameMaker games, as I've said before, tend to be very CPU bound, and that means that most of the time that it takes to put a frame on the screen is going to be consumed by GML doing things inside the central processing unit part of your computer, rather than on the graphics card, which is the other major player when it comes to games and how games perform. And this means that your graphics card really doesn't have a lot to do, and it's really just sort of sitting on the sidelines waiting for something to happen while the CPU does its thing, and the graphics card tends to be rather underutilized in GameMaker games, and your games tend to be very CPU bound. If you're doing regular 2D drawing in GameMaker using sprites and that sort of thing, and sprites and tiles and whatever, GameMaker will do some optimizations behind the scenes for you to make that less of a problem, to mitigate that problem. But when you're in the world of 3D, you're pretty much on your own, and you have to know to do some things yourself, and you have to know on a fairly deep level what your game is doing and how long those things that your game is doing takes, and what you can do to speed those up. Let's talk about graphics cards. So the TLDR for graphics cards, and this applies to anything that can be used to put graphics on the screen, whether that's a dedicated graphics card, like your NVIDIAs, your GTXs, your RTXs. I'm getting to the point where I can't remember all these abbreviations. Whether that's integrated graphics like you might see on a laptop. It's fairly common to see Intel integrated graphics on laptops, or AMD's kind of sort of answer to Intel's integrated graphics. I'm not going to get into it. It's complicated. APUs, which are basically graphics units built into CPUs that AMD occasionally sells. I'm just going to refer to all these things as graphics cards in this video. Please don't get upset at me in the comments. The way that each of these things work is that they can do a lot of very simple calculations very fast, and they're very good at doing them in parallel. Your CPU, your central processing unit, may have 4 cores in it. It may have 8 cores. If you have a really fancy CPU, it may have more than that. And that means that your CPU can do a couple things in parallel, and none of that's really relevant to GameMaker regardless, because GML is very, very single-threaded, and you can't really do parallel processing in it. But your graphics card, even a lower end or older graphics card, can have hundreds of cores, or even thousands of cores, and it can do hundreds or thousands of operations in parallel. And that happens to be very, very good for things such as putting graphics on the screen, because each vertex that you try to draw can be evaluated independently of all of its neighbors. Each fragment that you try to draw, also known as every pixel on the screen that you try to draw, can be evaluated independently of its neighbors. This is the sort of task that you can do in parallel very, very well. And the things that makes GPUs very good at their job is that they're good at breaking up the workload over hundreds or thousands or however many cores they have. And the reason that we're not utilizing that very well here is this line right here, Vertex Submit. This is going to submit a Vertex Buffer to the graphics card for drawing. Each of these individual trees are fairly simple. There's 6 planes, which are sort of radiating out from the center, and they have 2 triangles each. So that's going to be, 12 triangles total? And I ran that on the Raspberry Pi. Let me run that on Windows again. Each of these trees is going to have 12 triangles in total for a total of 36 vertices. And that's not very much. We are not giving the GPU a lot of work to do that it can do in parallel, that it can break up over its many computation units. As you can see, these trees are all very simple. There's not a lot to them. And I guess going back to the sports analogy, if our GPU is our best player on the team, what GameMaker is basically doing here is having the GPU sit on the bench for most of the game, except for just short intervals throughout the game where GameMaker brings the GPU in to make a play that ultimately isn't very complicated. I lost track of that analogy real fast. It's not a really efficient way to draw stuff is what this means. This is where the matter of combining things into a single vertex buffer comes into play, because then if we can combine every tree in the game into a single vertex buffer, we will not have to loop through this entire we will not have to loop through this entire array of tree data. We will not have to build its matrix. We will not have to submit its individual, relatively tiny vertex buffer 2,500 times. And all we'll have to do is submit a single vertex buffer with a lot of triangles in it. I believe there are 30,000 triangles total between, if there's 12 triangles in 2,500 trees, that's 30,000 triangles and 90,000 total vertices. I wrote this down before I started. I'm not going to do math in my head. And we can just submit that all at once, and the GPU will be perfectly happy to just swallow that and evaluate them all at the exact same time. Again, it can do it in parallel very well. and our CPU can just sit back and watch the best player on the team do its thing. So what this means is that it doesn't really matter to the GPU if you ask it to draw 12 triangles, or if you ask it to draw 100 triangles, or if you ask it to draw 1,000 triangles. It will be more or less equally happy to do each of those things in about the same amount of time. I say that for the most part because obviously these are computers with finite capabilities. You can't do anything infinitely in a computer in the real world. At some point, if you keep asking it to draw more and more stuff, the GPU will run into its limits of its own. But for what we're doing right now, we can do better than 12 vertices per tree. So let's get to combining these things. So in the create event here of this here camera, let me just because this is taking up a lot of space, and I'm going to want to scroll up a couple times. Let me collapse the creating the floor grid part of the code. We're going to loop through this array of trees, and we are going to process each tree again ahead of time before we get to the draw event. So I can do data equals tree data index I, much like we're doing in the draw event here, where we're looping through each tree and drawing them based on the data that's stored in there. This, of course, is just a reference to this struct that we have created, containing the model, the x, the y, the rotation, and all that. Next, I'm going to create myself a vertex buffer, VB. I'm going to call it combine, and that's going to be vertex create buffer, vertex begin, VB underscore combine. The format that it's asking for is going to be this vertex format that's described up here. I'm just going to call that vertex format. We will be getting back to the vertex format in a minute. And at the end, when we're done, vertex and VB combine. So vertex buffers. Unfortunately for us, as of my recording this on the 14th of April in 2021, Common Era, GameMaker does not have a built-in way to allow us to access the contents of a vertex buffer directly. So instead, we are going to have to convert it to a regular buffer if we want to be able to get to the stuff inside it, and if we want to be able to combine each of the vertices. And we can do that with the vertex create buffer from buffer. And that's going to take a source buffer, which is going to be the vertex buffer, which is going to be data.model, because when we initialize them up here, the model is set to VB underscore tree. So my Raspberry Pi just went to sleep, and I prefer that it doesn't do that while I'm recording. Data.model. The format is going to be... oh god, I got this backwards. We can say buffer create from vertex buffer. This is the handy function that GameMaker provides for allowing us to go from a vertex buffer to a regular buffer, and allows us to do all the things to the contents of a vertex buffer that we would do with a regular buffer. Keep in mind that it does create a copy, so if you want to make changes to the buffer and you want to then draw it on the screen, you will have to go the other way around and vertex create buffer from buffer. These function names are horrendously long, but we will not be using that right now. I did in the past, and I'm sorry to all the people who dislike having to watch like 3 or 4 or 5 prerequisite videos before you watch this one, but I did in the past, about a year ago, make a video on vertex buffers and some of the advanced things that you can do with them, including converting them to and from regular buffers. If you want to hear more about how that works, I will have a link on the screen right now. Perhaps a little bit more relevantly, I have also made videos on regular buffers and the things that you can do with them, just as far as raw data goes. And I would also definitely recommend watching those. Again, I'm sorry to all the people who dislike having to be jumped around and watch other videos like this, but this is a complicated topic, and you really can't talk about it in isolation without talking about a bunch of other subjects in GameMaker and in computers. And if you think I'm going to try and cram all that information into this video when I've already gone over it, well, let's just say that that's not going to happen. So buffer create from vertex buffer. It takes a couple arguments. It takes the vertex buffer. That's going to be data.model, which is going to be this member of the struct, which we're defining up here. That's going to be VB underscore tree, which is just going to be a reference to the vertex buffer that you get from the load model function. It's going to take a type, which is one of the buffer types. That can be buffer fixed, it can be buffer grow, it can be buffer wrap. You can use any of those, just don't use buffer fast, because buffer fast will not work with what we want to do. I'm just going to go with buffer fixed.
Hey.
And the alignment, I'm going to make that 1. Theoretically, you can do 4. I'm not gonna do 4. Because buffer alignment is a thing that tends to lead to trouble when you set it to something that is incompatible with what you're trying to do, and I'm going to just leave it at 1. So, let's talk about the vertex format for a minute. So this is a pretty standard 36-byte vertex format. You have a 3D position. A 3D position is composed of 3 32-bit floating point values, so it has a 32-bit floating point x, a 32-bit floating point y, and a 32-bit floating point z. Those are 4 bytes each. 32 bits, 4 bytes. And if you have 3 of those, that takes up 12 bytes. Next, you have a 3D normal. And this is very much the same thing. It's 3 32-bit floating points, so that's another 12 bytes. Next, you have a 2D texture coordinate. And those are going to be 2 32-bit floating point values, so that's going to be 8. So if you're keeping track, the size of the vertex format is going to be 12, 24, 30, 2. I can add. And the color is going to be, depending on how you look at it, either a single 32-bit integer or 4 8-bit integers. And either way, that's going to be another 32 bits, or 4 bytes. And the size of the vertex format is going to be 36 bytes in total. And this is important because this is going to affect exactly how we combine the stuff in the vertex buffer. So I'm going to create myself a second for loop. Yes, I know, nested for loops, they can be scary slow, but for var j is going to equal 0, j is less than buffer get size. I need to save this to a variable myself, don't I? We can call it, I'm just going to call it raw data. And then j++ at the end. Actually, it's not going to be j++. That was a, that's not going to work. We're going to say j plus equals 36, because 36 is the size of the vertex format. And then, of course, when you're done with the buffer, this is not going to be cleared away from memory when you're done with it automatically, so you have to buffer delete raw data when you're finished. Yes, I know, this is not the optimal way to do a for loop in GameMaker. In fact, for loops themselves aren't the optimal way to do loops period in GameMaker, but I don't care. That's a micro-optimization. That's a subject for another day. So we're going to be stepping through this buffer 36 bytes at a time, and the data that you see in the vertex buffer is going to be exactly what I just described. So it's going to start, if you think of the value j as the beginning of each vertex, it's going to start, I'm going to say var xx is going to equal buffer peak raw data. The offset is going to be j, and the type is going to be, as I said, buffer float 32. If you want, you could use buffer read for this, and then you won't have to deal with the offset. The read-write position will update automatically, but I'm going to be using buffer peak because I want to make it more clear about what the things in each position in the buffer are consisting of. Next, var yy is going to equal buffer peak raw data j, but instead of just j itself, which is the beginning of each vertex, it's going to be j plus 4. The x coordinate is the first position in the vertex, and it takes up 4 bytes. So the y is going to be the second thing in the vertex in the buffer, and it's going to start at position 4. If you want to make it a little bit more clear, we can say xx is going to equal the thing at buffer position j plus 0. That may or may not help. Y is also going to be a buffer 32-bit float. Z, I'm going to start copying and pasting because this is going to be very much the same. Z is going to be another 32-bit float at position 8. Next, we have the normals. The normals are, again, very much the same. Normal X is going to be at a 32-bit float at position 12. Normal Y is going to be a 32-bit float at position 16. I'm guessing everybody is aware of this, but there are 8 bits in a byte, so if you have a 32-bit float, that's going to mean it takes up 4 bytes of memory, because 32 divided by 8 is 4, and Z. If you've gotten this far into computers, I'm guessing you already know that, but regardless. The X texture coordinate, again, after it comes after the normal, that's going to be j plus 24, another 32-bit float. Y text is going to come after the X text, or if you prefer, you can call them U and V. Is often terminology used when it comes to texture coordinates, but I think X and Y are fine. And lastly, there's the matter of color. And color is not a 32-bit float. As I said, you can look at this from the perspective of a single 32-bit integer, but shut up, phone. Instead, I'm going to read these out a single byte at a time. Raw data, J plus 32 is the next position. And buffer, instead of buffer F32, we're going to be looking at a buffer U8. And colors in GameMaker and in computers in general are generally stored in the form of 8 bytes for red, green, blue, and alpha each. So we're going to have 1 byte for red. Let me copy that. A new 1 byte for green, which is going to be J plus 33. 1 byte for blue, which is going to be J plus 34. And 1 byte for alpha, which is going to be J plus 35. So alpha, this value that this contains is going to be from 0 to 255 because it is an 8-bit integer, an unsigned 8-bit integer. Generally, when you deal with alpha in GameMaker, you would instead rather have it from 0 to 1, with 0 being fully transparent, 1 being fully opaque, and 0.5 being somewhere in the middle, about 50%. Whereas what we're getting right now is going to be 0 for fully transparent, 255 for 0 for fully opaque, and 127 for somewhere in the middle, 50%. So instead, we can just divide that by 255. That will normalize the value between 0 and 1, and that will allow us to use that in colors for GameMaker functions regarding color. So this is the data, but we still have to do something with it. First, we can well, I say first. All we really have to do now is add it back into the combined vertex buffer. Vertex position 3D VB underscore combine. This is going to be, everything is going to be added to the same vertex buffer, so every tree is going to be added to the same vertex buffer. The X position it's asking for is going to be XX, Y, and Z. Vertex normal VB combine. Normal X, normal Y, normal Z. Am I missing something? Nope, just took the syntax checker to take a moment to catch up. After that, vertex text chord VB combine, X text, Y text, so that's going to be the U and V. And lastly, vertex color. You can spell color with or without the U, it doesn't really matter. VB combine, they're just aliases for each other. The color is going to be make color RGB, taking red, green, and blue. And the alpha is just going to be the alpha. Okay. So this isn't going to exactly work, and some of you probably know why. If you don't know why, just give it a minute. I'm going to take a drink of water. And that should be enough time to let you think about it for a moment. For one, I'm not actually doing anything with this yet. I need to actually draw the vertex buffer in the draw event. There's no point running the game when I'm not doing that because it won't affect the outcome. I can say vertex submit VB underscore combine. The primitive is going to be PR triangle list, and the texture is going to be sprite get texture SPR tree subimage 0. If you want, you can set the world matrix to the identity right before you draw this, but there's really no point because it's already been set when you finish drawing the player. I'm going to run the game now. And you're going to see that the world is actually quite empty except for a single tree that's sitting right here at the world origin. The frame rate has gone up considerably. It's gone up from 200 and change to almost 1500. The average FPS real. And that's a pretty big jump, but it's not very useful to us because all the trees have actually just disappeared. Fortunately, the game is actually drawing every single tree in the game. It's drawing just as many vertices as it was before. But they're all in the same place. All 2,500 trees are just layered right on top of each other, one on top of the other, right here in the world origin. And that's because instead of doing anything really of interest to each of the vertices when we put them into the combined vertex buffer, We're just putting them in at the exact same position that they originated from, which is just going to be the positions that they exist in the 3D model file, basically. And they have not been translated, they have not been rotated, they have not been anything as before they're being added. So let's do that. So there's a handy function called matrix transform vertex in GameMaker. And this allows you to transform a matrix based on a transform matrix, so translation, rotation, and scaling. And it allows you to calculate exactly where in the world it would end up after going through such a translation. If you've ever looked at the vertex shader in a shader and seen the input position being multiplied by the world matrix or by the projection matrix or by all three matrices, that's what's going on here. That's what the shader is doing. In this case, this function just lets us do basically the same thing in GML. So to start with, we need a matrix, and we can figure out a matrix. I can say matrix is going to equal matrix build. We can give it a translation of data.x, data.y, because that's what we are defining up here in the tree data structs. So it has an x, a y, and a rotation. These trees are supposed to basically lie flat on the ground. They're supposed to lie flat on the xy plane, so we can give a z value of 0. No rotation on the x-axis, no rotation on the y-axis. The rotation on the z-axis, I guess I can just look at it here. We can copy what's going on in the for loop, which is commented out right now. The rotation on the z-axis is going to be data.rotation, and the scaling is going to be 1, 1, 1. We are not doing any scaling here. And this is our matrix. We don't have to set it to the world matrix or anything like that, but we do have to pass it to the matrix transform vertex function, matrix. And next it's going to take an x, a y, and a z position. That is going to be x, x, y, y, z, z, which is the position of each vertex untransformed. And this is going to return an array of 3 values. So this is basically going to be a vector 3. Instead of being a struct or anything like that, it's just going to be an array of 3 values with the first value being x. As you can imagine how this works, the second value being y, and the third one being z. So I can say var, let's say transformed position is going to equal matrix transform vertex. Matrices, by the way, these are just arrays. Arrays are garbage collected by GameMaker. You don't have to destroy them or anything the way that you have to delete a buffer when you're done with it, or a data structure of some other sort. And now, instead of saying vertex position 3D with the original x, y, and z positions, we can say vertex position 3D with transformed position starting with index 0. I'm just going to copy and paste because this is a long variable name that I don't feel like typing out more than once. Again, index 0 is x, index 1 is y, and index 2 is z. Now if I run the game, this is going to look a lot better. Still not going to be perfect, but it's going to look a lot better. And you can see that each of the trees is indeed being drawn, and they're being lit by the spotlight, which is right here. And all right, so we've still got our forest. It is now being drawn at 1300 FPS real on average. That's slightly lower than when they were all layered on top of each other, because now the trees are actually being drawn and all the fragments in them are not being discarded the way that they were when they were all being drawn on top of each other. And this means that the fragment shader has a little bit more work to do, particularly with the lighting calculations. And there's also the fact that the longer that I record videos, my games tend to slow down as my computer spends a lot of time recording video and heating up and throttling itself, but that's probably not a very major factor. Anyway, we have 60 frames per second. My voice is starting to go because, as I said, I've had to record this video like 4 times, and these have been pretty long recordings, so I'm going to try and wrap this up quickly. Let me run this on the Raspberry Pi. So unfortunately, boy, I don't know if I'm going to end up sounding different now than I did when I started, but I really sound different in my head because I've been talking for 3 hours. Let's switch this to the Raspberry Pi and run the game. I've been drinking water too, pretty much all afternoon, just to try and mitigate this problem, and yet, come on. Okay, so we're seeing a couple things happening. One is that the actual FPS of the game hasn't really changed that much. It was about, I want to say, the low 20s the first time I ran the game, and it's still about low 20s now. But the FPS real that you're seeing has gone up considerably. The FPS real has gone up from 20 or so to now about 120, about 6 times. And that is because of what I said before with regards to CPU bound versus GPU bound. Previously, when we were trying to draw the entire scene in a for loop like this, the game was very CPU bound because the computer had to execute a lot of GML, and the graphics card didn't really have a lot to do. But now that we've combined all these vertex buffers, that has flipped on its head, and the game is now instead rather GPU bound because it's doing a lot more on the GPU than it was before. For a desktop computer with a dedicated graphics card, it's not that bad, and you see a rather dramatic improvement. My GTX 1060 can swallow 30,000 vertices fairly easily, but the Raspberry Pi has a considerably weaker graphics unit inside it. I don't know its specs off the top of my head, but the graphics chip on the Raspberry Pi is considerably weaker, and now the game is having to spend a lot of time waiting on the GPU for it to do its calculations, leaving the CPU with not a lot to do. Which is why the FPS real has gone up, but the FPS that we're actually observing hasn't really changed. Alright. I am going to have, like, no voice tomorrow. This is horrifying. I don't usually spend this much time talking in a day. There is a slight problem, and that is if I were to switch back to Windows. Rotation for the normals is not taken into account, and this can have implications for lighting. You see the spotlight is stationed at about where I'm standing right now, and it's pointing about to the world origin. And some of these trees are lit correctly the way that you would expect them to be, whereas other trees are not. And that is to do with rotation. The normals in a vertex, as you probably remember, have to do with how lighting is evaluated on each vertex and on each fragment. And you can see that, for example, some of these trees you would think are in fairly direct sunlight and should be lit. For example, this plane of this tree that's right in front of me. It's pretty much right in front of the spotlight, and you would expect it to be fully lit, but it's really in shadow, whereas this plane that's, this one here is more parallel to the direction that the light is going in, and you would expect it to be darker, but it's, instead this one is almost fully illuminated. And that's because of the way that the normals of the tree are set. And when you rotate a object in space, you also have to rotate its normals if you want the lighting to be appropriately affected. Again, if you've ever looked in a 3D lighting shader, in the Vertex shader, you have probably seen the input normal being multiplied by the world matrix as well, and that would transform the normal accordingly. On the subject of other videos that you should probably watch if you want to fully understand this one, I did make a whole series of videos last summer about 3D lighting shaders, and I talk in fairly extensive detail about how normals work in that video, and you probably would like to see that if you haven't already, because probably the rest of this video is going to be talking about normals. Alright. So, we can, if we wanted to, do the same thing to the normals as we are with the positions, but instead of transforming the... Stop hitting S instead of Control S. Instead of transforming the positions, we are transforming the normals, and that might allow us to do something like this, and use the transformed normals in the vertex normal part of the vertex building instead of the position. However, if I run this now, this is gonna actually look really weird because this is not quite what we have to do, and that is because yeah, this tree is fully illuminated. This looks fairly wrong. And that is because when you transform normals in space, you actually don't want to transform them with translation, which is data.x and data.y. If you were to do this math in the Vertex shader, you would use the homogeneous coordinate of 0 in order to account for this and prevent the normal from being transformed and keep its unit length as 1. But we don't have the ability to do that directly here in GameMaker, so instead I'm going to say matrix normals is going to be matrix build with the position removed. So 0, 0, 0 on the position instead of the tree's position. Rotation can stay the same, scaling can stay the same, and instead of matrix transform vertex with the first matrix, we can say matrix normals. This is going to be better. There is still room for possible error in here. Well, for one, if I look at the at what you see in the world. This looks much better. The correct faces are lit. These faces are somewhat more parallel to the light, and they are not receiving as much light, although they're still receiving a little bit. Same thing back here with that tree in the distance. If I were to, let's see, instead of having the spotlight pointing in the same direction, I'm gonna say decos we are going to have the spotlight rotate, and you will see that the other trees around it can be appropriately lit as well. Let's see, it's like a searchlight for a lighthouse or something now. Anyway, you can see that the other trees are appropriately lit. There's still the matter of scaling. If you were to scale a vertex by a non-uniform value, so not the same value on the X, Y, and Z scale, you run the risk of your vertex, of your normal not being normalized, so its unit length not being 1. And if you don't do that in your vertex shader, that can cause other issues with the way lighting is calculated. You can normalize a vector yourself fairly easily. You can divide each of its components by its unit length. So that would be something like transformed. I'm going to call it var. I really need to start using shorter variable names. The unit length is going to be the 3D distance between 0 and the point, and normal. Help, copy paste. This would normalize this vector so that its values all have a unit length of 1. Normalizing vectors is probably a subject for another day, but in case you are curious, if I run the game now, it's going to have the pretty much the same. It's going to look the same as it did before. Okay, that's everything I wanted to do here. So we now have some code that can combine multiple trees into a single vertex buffer. There are some situations that I alluded to earlier in which this may not work. One is that this is predicated on all of the buffers that you're combining, so all of the trees not moving, like ever. If you were to draw them all individually, you could update their position. You could have the trees move around. You could have them like sway in the breeze or something fairly easily. Well, maybe that last one wouldn't be too easy, but you could still do it. But when they're all fused together into a single vertex buffer, over like they are here, these trees cannot move. You can do a limited amount of animation using a shader, but that is an advanced topic for another day. And this is something that you can really only do if you can count on these objects never moving. So it's not really great for things like NPCs or enemies or that sort of thing that have to move around, but for things such as trees, or for things such as buildings or walls or that sort of thing, it can be very, very good indeed. The terrain, if you have like different terrain features, you can probably get away with batching them into a single vertex buffer this way. The other situation in which this will not work very well is if each of these trees has a different texture. I do not have an example for this setup right now, but if you had multiple trees, that use multiple textures, specifically textures that live on different texture pages, this will not work very well because you can only, you can only easily submit a single vertex buffer with a single texture. You can do a little bit of magic with texture stages to draw things with multiple textures, but that's also a story for another day. So if you had multiple different tree types, if you had a handful of different tree types and all of those sprites lived on their own texture pages because we're doing 3D and that tends to be easier, then you will not be able to combine every tree in the game into a single vertex buffer. At most, you could only combine every tree in the game that uses the same texture into their own vertex buffers. And that can still be a pretty dramatic improvement, so instead of drawing 2,500 trees, maybe you'll only be drawing, say, 5 or 10 vertex buffers with a bunch of trees in them. But if you try to combine objects that use different textures into a single vertex buffer, at best, they'll all just use the same texture and they'll all just look like the same tree, even though you don't want them to. And at worst, if they're dramatically different, it could cause some very glitchy looking texture effects, with texture mapping being all kinds of messed up. Combining textures is sort of an extension to this that I want to talk about later, but honestly, I really want to stop talking right now. And it's probably going to be its own fairly lengthy video, so that'll come later. Anyway, I'm just going to run this again just because of how satisfying it is to see this running at like 1200 frames per second real or whatever it was earlier. All these trees. This was really the first thing that I did in GameMaker in terms of optimization. The first time I discovered that you could do this back in 2015, 2016, it was really quite mind-blowing how much more you could actually draw in a 3D scene in GameMaker like this than I had originally thought. And those were back in really the days of GameMaker 8. I was still using GameMaker 8 when I was experimenting with that for the first time, but the basic principle is the same. Just instead of using the D3D models, you would use a Vertex Buffer. Anyway, I am going to go stop talking and probably make like a cup of tea or something because I really need that. My name is Michael. I hope you all found that interesting. In the future, we will be talking about other 3D optimization techniques. I know I said I was probably going to post those videos on a basis of kind of whenever, but I've turned out to have a lot less time to do planning for other videos than I really expected to recently, so I'm probably going to actually post a couple of these in a row because they tend to be more straightforward, and I don't need to spend 2 days planning to make them. Optimization is fun. You can definitely go overboard, and you can definitely spend all your time optimizing and never make your game, but it can be a lot of fun in its own right. Anyway, I have a Patreon, so if you want my voice to recover, go and check the link in all the usual places for that or something like that. I'm not sure if that's how this self-promotion is supposed to work, but otherwise I try to post about 2 videos a week. One of these and one to let's make a tower defense game, although that may also be on hold for a little while because it's, again, time, and that tends to be a bit of a lower priority item. Otherwise, if you want the code for this, look for the GitHub repository in the video description. I hope you all found that interesting, and I will see you all later. Special thanks to Kiara Elizabeth, Connor, David Key, Edward Holt, Emily Koyo, Posho, Tusk, and Zenith for supporting these videos. If you want your name in the credits or to hear yourself shouted out at the end, head on over to the Patreon page down in the video description to join the fun.